Welcome to Chapter 12, Simple Linear Regression. Here in Chapter 12, we're going to cover simple linear regression. We're not really going to get into multiple linear regression. We're going to explain a little bit about the least squares model. Regression is primarily a way that you can predict something. The something that you're trying to predict is referred to as the dependent variable. It depends on an independent variable. You change the independent variable and you expect it to cause a change in the dependent variable. What you do with least squares method is you look at the sum of the squares of the differences between the actual values of the dependent variable and what's predicted by the regression model. A statistic that's quite useful in determining whether or not you have a good model is called the coefficient of determination. It also serves as a bridge between a correlation problem and a regression problem. In a regression problem, you're trying to use one variable to predict another one. In a correlation problem, you're primarily just wanting to see whether or not the two variables, whether or not they're strongly related to each other. Managerial decisions can be based upon the relationship between two or more variables. I actually had a student one time that brought me a manual that they gave to managers for a franchise. It was a restaurant. These people used it to manage the managers. It showed a graph with the relationship between the sales for different restaurants and the other variable that was in there besides the sales was something that they referred to as the upfront cost. And the upfront cost was an item that was directly controlled by the managers. And how the managers controlled that upfront cost based upon the size of the operation, which was measured by the sales, they were evaluated on that. And they'd set up a regression model, and they really used it to manage their managers. But regression analysis allows you to develop an equation so that you can make predictions, you can evaluate, in some sense, how good those predictions are going to be. The dependent variable, what you're trying to predict, is usually denoted by y, and the independent variable, the variable that you're changing in order to create an effect in that dependent variable, is usually referred to as x. Now, it would be nice if we had enough time to where we could get into multiple regression, where we could look at different independent variables and what their effect is upon a dependent variable. But we're only going to have time to look at the simple case. The simple case just involves a single independent variable and a single dependent variable. We represent that relationship with a straight line. That's why it's called linear. Linear is just a line. So we're going to have a slope, we're going to have a y-intercept. And the regression model, we use the least squares technique in order to come up with the best values that we can for the slope and for the y-intercept. The equation that shows you how y is related to x, which includes the random error term, is referred to as the regression model. So y is equal to beta sub 0 plus beta sub 1 times x plus epsilon. Epsilon is the character that kind of looks like an E, but it's the Greek letter epsilon, and it's the random error term. Beta sub 0 is where it crosses the y-axis, and beta 1 is the slope. It's a change in y over the change in x. Now they're referred to as the parameters because this is the population relationship. Now let me give you an example of this. Suppose that x is the square footage in a house, and the y is what you're going to pay for the house. That's the selling price. Let's say it's in dollars. So if the x value is 2,000, you have a 2,000 square foot house, You could plug in 2000 for x, and if you know what beta 1 is, and if you know what beta 0 is, you can come up with a predicted value for the selling price. Now, the problem is that you can have two different 2,000 square foot houses, and they're going to sell for different amounts of money. That's what the epsilon's for, that random error term. It could be a little bit less than where that line projects, or it could be a little bit more. But when you look at the expected value of this relationship, the expected value of the random error term is 0, and that part just disappears. The simple linear regression equation, when you take the expected value of y, you're going to get beta 0 plus beta 1 times x. The epsilon part, the random error, it just disappears when you look at the expected value. And it's just a straight line. The beta 0 is where it crosses the y-axis. It's the y-intercept. If x is equal to 0, then the expected value of y is going to be beta 0. You plug in a different value for x other than 0, and that's where the slope takes effect. The beta 1 is the slope of the regression line. Now back in chapter 2, we looked at two variables, two quantitative variables, an x value and a y value. And we could plot the points, and then we'd have some idea as to whether the relationship, whether it was positive or whether it was negative. We're going to use the least squares technique to come up with the equation for the line, but in general, if you have that upward slope, you're going to have a positive relationship. But you can have a downward slope, you can have a negative relationship, or you can have no relationship. When I was an undergraduate in college, I worked sometimes in a bike store. And back then, bicycle helmets, they pretty much cost the same amount of money. There weren't a lot of different brands, and they're pretty much all the same thing. But I was looking into buying some bicycle helmet for some of my great-grandchildren, and I looked in this store, and they had one bicycle helmet that was a lot more expensive than the others. So I just asked the people in there, I said, why is this one so much more expensive? And they said, well, pick it up. And so I picked it up, and it didn't weigh hardly anything. It says it has the same level of protection as the others, but it's made out of lightweight materials. And I checked prices on the internet, and I found out that generally speaking that was true. If you had certified helmets, ones that were certified to be able to protect your skull in case of an accident, if it weighed less, they tended to cost more. And this illustrates that kind of relationship. If X is the weight of the bicycle helmet, as the weight increases, you don't have to pay as much for it. But if you want to buy a lightweight helmet, it's going to be more expensive. Now, to give you an example of this relationship to where there's really no relationship, I heard a pretty good example here the other day. If you look at the height of an individual and look at what their IQ score is, if that X, that horizontal axis, represents the heights of individuals, you have short people, you have tall people, but you'll find, generally speaking, that their IQ scores tend to just go up and down. You'll have some short people that are really intelligent, and then you'll have other short people that aren't that intelligent. Same thing for tall people. But the Y value is going to go up and down as the X value increases, and everything just kind of balances out, and you end up with a slope of 0, which would indicate that there's no relationship between those two variables. The estimated simple linear regression equation is y hat is equal to b0 plus b1 times x. Y hat is what you say when you look at that symbol, the y with the caret on top of it. b0 is the intercept. b1 is the slope. In the population model, or the regression model for the problem, we use beta 0 and we use beta 1. But in the sample model, in this estimated simple linear regression equation, we use the b's rather than the betas. Now the y hat is the predicted value or the estimated value for a particular value of x. Now here they're changing the notation a little bit. They're putting a subscript of I. Y sub I is just some y value that's in your data set, and then y sub I hat, the one with a caret on it, is what you would get when you predicted the value based upon the x value that corresponded to that y value. But the difference between the y value, that's actually the y value that you observed in the data set, and then the y sub I hat is the predicted value. The difference between those two is the error. So when you take the errors and you square them and add them up, you have the sum of the squares of the errors. And what you want to do is to make that as small as possible. And that's why it's called the least squares technique. We're going to minimize the sum of the squares of the errors. Now another name for the difference between y sub I and y sub I hat, it's also called the residual. You've got the sum of the squares of the residuals that you're minimizing, but it's called the least squares technique. And you can use calculus and figure out the equations for the slope and for the y-intercept that's going to make this quantity, this sum of the squares of the errors, that's going to make it as small as possible. And in that sense, it's the best line that you can come up with for a set of data when you want to try to get the points as close as possible to the line. When you want to minimize the distance between the actual y value and what's predicted by the model. In some sense, that's going to be your best model, is the one that has the least sum of the squares of the errors. Now we're not going to get into the particulars of how you come up with this formula, but it's based on calculus. When you take the sum of the squares of the errors, and if you look at that as being a function of two variables, it's a function of the y-intercept and the slope, and you can use something that's called a partial derivative. You can take the partial derivative of that expression with respect to the y-intercept, set that equal to 0. Take the partial derivative of that expression with respect to the slope and set that equal to 0. And you come up with two equations and two unknowns. And you can solve them simultaneously. And one of the techniques that you can use for that sort of thing is called Cramer's rule. And if you use Cramer's rule on that system of linear equations, you can come up with a formula that's pretty close to this one. You can get the slope that's going to minimize the sum of the squares of the errors by taking the sum of the products of the deviations of x from its mean and the deviation of y from its mean. Now we use this numerator part of it, we used this back in chapter, I think it was chapter 3, is where we calculated the covariance. But you could take the numerator part and divide it by n minus 1 and you had the covariance. Now the denominator, I just refer to it as the variation in x. It's the sum of the squares of the deviations from the mean for the independent variable, for the x. That number is used in the calculation of the standard deviation of x. But you take the sum of the squares of the deviations from the mean, you divide that by n minus 1 and take the square root and you have the standard deviation. But all we need to calculate the slope is we need that numerator in the covariance, and then we need the numerator in the variance calculation for the x's. The numerator is referred to by some people anyway as the covariation. you take the covariation in x and y and divide it by the variation in x, and that will give you the slope. X bar and y bar, those are the means for those different data sets. Now, straight lines are pretty well behaved. If you know the slope of a straight line, if you know any point that's on that straight line, then you can find any other point. Now, it turns out that when you look at those errors, when you look at the sum of the errors, that it's always going to be 0 when you use the least squares technique. And there's an infinite number of lines that will give you that property that the sum of the errors is going to be 0. All you have to have is that that line goes through the average values. If you figure out what x bar is, and if you figure out what y bar is, that's a point. And you can put any line that you want to that goes through that point, and it's going to have the property that when you add up the errors, when you take the difference between y and what's predicted by the model and calculate all of those errors, they're always going to add up to 0. So we know that that x bar, y bar, that's going to be a point that's on that straight line. And we can use the previous equation, take the covariation in x and y, divide it by the variation in x, and we can come up with the slope. And then we can use this little formula and figure out what that y-intercept is. If you take y bar, you take the average y value and subtract the slope times x bar, that'll give you the y-intercept that's going to minimize the sum of the squares of the errors. Now, this is a fairly simple example to illustrate simple linear regression. This auto sales place, Reed Auto Sales, they have a week-long sale every once in a while, and right before they run the sale, they do some advertising. They buy some television ad spots on the weekend before the sale. And they've done this previously, so they take a random sample of 5 times in the past when they've done this and gather the data. And this slide shows the data. We're going to treat the independent variable as the number of TV ads because they get to choose that. I can have 1 ad, I can have 4 ads, I choose that amount. The dependent variable, we're assuming there's a relationship, and we're going to set this up as a linear relationship. But we're assuming that the number of cars that were sold, that's going to be the y, depends upon the number of TV ads. And then we're going to try to see what that relationship is if we model it as a straight line. So this slide shows the sum of the values. There were 5 of the x values, the TV ad values. So 10 divided by 5 would be 2. The sum of the number of cars sold is 100. There are 5 occurrences in the data set, so 100 divided by 5 would be 20. So the x bar value is 2 and the y bar value is 20. Now, we're not going to go through this problem taking those fundamental definitions, figuring out what the covariation is, figuring out what the variation in x is. We did that sort of thing back in Chapter 3 when we calculated the covariance. But here we're going to use Excel to come up with the answer. So to begin with, all you have to do is just open up an Excel worksheet, and you can put some labels in there. In B1 we put TV ads, in C1 we put cars sold, and then just enter the 5 values in there. So we have the data values for the independent variable in column B, and we have the data values for the dependent variable in column C. Now all you need to do is to click on the Data tab up at the top. If it's been added, the tool pack, you can access it up at the top under the Analysis group. Inside the Analysis group, you should have an entry up there called Data Analysis. And all you have to do is just click on that Data Analysis and go down to the R's, all the different tools there in alphabetical order. Just go down to the R's and double click on regression, or else just click on it, select it, and then click on OK. The next couple of slides illustrate the steps that you go through to use the regression tool in Excel, but I thought it would be better if you had a video that actually shows the entire process of it. So there's one out there that's called TV Ads versus Cars Sold Regression in Excel 2016 video. But if you look at that one, it's going to show you kind of a more continuous display of how to go through and get Excel to do a regression for you. The video shows doing this a little bit differently than it's explained in the steps here. For example, it says select the confidence level. If you want a 95% confidence level, you don't really need to select that. You're going to get that one by default. As a result of the regression on the data up at the top, you get the summary output that starts in A8. It's basically broken up into three parts. The top portion, which starts in row 10, are the regression statistics. The middle portion is an analysis of variance table that starts in row 17. And then the third portion, which begins in row 23, gives you the coefficient information. I just refer to this as the coefficients table. The bottom left-hand portion of the regression output is where it shows the value for the slope and the intercept, the regression coefficients. This slide shows you the formulas. You figure out what the slope is by taking the covariation, which is the sum of the products of the deviations of x from its mean and y from its mean, and divide that by the variation in x, the sum of the squared deviations from the mean. If you apply it to this particular data set, the covariation is 20 and the variation in x is 4. And so when you divide that out, you get a 5. But Excel just gives you the number. If you know what the slope is, you can take the average y value, which was 20 in this case, and take the average x value, which was 2, and multiply the slope times the average x value and subtract that from the average y value, and that'll give you the y-intercept. Now we're not going to cover the formulas for the standard error of the intercept, the s sub b sub 0, or the standard error of the slope. But you use those numbers in order to calculate your t-statistics. You take the slope and subtract the hypothesized value of the population slope and then divide it by the standard error of the slope to get your t-value. And you can use that to test to see if there's a linear relationship between the independent variable and the dependent variable. The p-value is for a two-tailed test. Under the null, you assume that beta 1 is equal to 0, and under the alternate or the alternative hypothesis, you're trying to show that it's not 0. But if you take that t-value and it's n minus 2 degrees of freedom, in this problem the sample size was 5, so 5 minus 2 would be 3. But you take that t-value and use it as the first argument, degrees of freedom as the second argument, and the t.des.2t will return the value, the p-value, the two-tailed p-value. And then you can compare that to alpha to make your decision. Now you can do precisely the same procedure if you wanted to test the intercept. But testing the intercept isn't going to tell you whether or not there's a relationship. All it's going to do is to tell you whether or not the line, the population line, does it pass through the origin. If it passes through the origin, then you can accept the null hypothesis. But if it's crossing the y-axis at some positive location or some negative location, then you're going to have enough evidence that you're going to be able to prove that it's not 0, that beta 0 is not equal to 0. At the bottom of a basic regression, you have the coefficients table. Intercept just means the y-intercept. And if you look at the coefficients column, in this case it's in column B, the value is 10. So the value of the y-intercept is 10. The value of the slope is right below it. This is the value that you multiply times x. X in this case is the TV ads. We're trying to predict the number of cars sold based on the number of TV ads. So if you take 5 times the number of TV ads and then add in the y-intercept, that's the predicted value for the number of cars sold. Now, if the question is, if Reed purchases 3 TV ads, what's the estimated number of cars sold? Well, you just take your estimated regression equation, y hat, which represents the predicted value for y. Y hat is equal to b0 plus b1 times x. b0 is the y-intercept that you get from your sample. b1 is the slope that you get from your sample. So the y-intercept is 10, the slope is 5. And you want to figure out what's the estimated value for y if x is equal to 3. So you just plug in 3 for the x. So we'll have 3 times 5, which is 15. You add the 10, you get 25. So we expect to sell 25 cars if there are 3 TV ads. Now, another way that you can use the information in the coefficients table is to test to see if there's a significant linear relationship between your independent and your dependent variable. Now, in this problem, we're trying to predict the number of cars sold based on the number of TV ads. So a logical question is, at some level of significance, and here I'm posing it at the most common level, at the 5% level, at some level of significance, is there sufficient evidence that a linear relationship exists between whatever x is and whatever y is? In this case, we're looking for a relationship between the number of TV ads and the number of cars sold. Now, all you have to do is to test the population slope. The symbol for the population slope is beta 1. If beta 1 is 0, you're multiplying 0 times the independent variable. So whatever the value of the independent variable is, it won't matter. If you're multiplying it times 0, it just disappeared. It doesn't matter whether you have 3 TV ads or whether you have 35,000 TV ads. You're multiplying it times 0 and there's no effect. The alternate hypothesis, or the alternative hypothesis, is what we're trying to show. We're trying to show that there's a relationship, that when you change the value of x, it's going to have an effect on y. And that means that your population slope is not 0. If you multiply it by 0, it doesn't matter what the number is. But if the slope value is not 0, it's going to have an effect. There is a relationship. And the way you can test this is with the t-distribution. Now this one's going to have n minus 2 degrees of freedom. It's not n minus 1. n minus 1 is used when you just have a single data set. But here we're looking for a relationship between an x and a y. We have 2 variables. It's in 2 dimensions. So you have n minus 2 degrees of freedom. But t at n minus 2 degrees of freedom is equal to the slope that you get from the sample minus the population slope divided by what's called the standard error of the slope. Technically, that denominator is referred to as the standard error of the regression coefficient, B1. But since B1 just represents the slope, it's commonly just called the standard error of the slope. And if you look in your coefficients table, that second entry, it says standard error when you see all of it. Here it's in column C. There's a standard error for the y-intercept, and there's a standard error for the slope. Now, under the null hypothesis, we're assuming that beta 1 is 0. So you just plug in 0 for beta 1. The value of the slope is 5. That's in B25. So you take 5 minus 0 and you divide it by the standard error of the slope. And that value is the 1.08012. That's in C25. When you do the arithmetic, the t-statistic is 4.6291, and that's in column D in row 25. Now, to see whether or not that result is at a significant result, you can look at the p-value that's in the same row. The p-value for that particular value of t is 0.01899. And the rule when you use p-values is if the p-value is less than or equal to alpha, then you're going to reject the null. So since alpha is 5% and this p-value, it's between 1% and 2%, it's almost 2%, but it's still smaller than 5%, so you're going to reject the null. When you reject the null, you have sufficient evidence to prove whatever it is that you're trying to prove. And here we're trying to show that the linear relationship exists. So we have been able to prove that there is a relationship between the number of TV ads and the number of cars sold. So since we were setting this up with a linear model, we've shown that there's a linear relationship. Now, if we had been trying to do this at the 0.01 level of significance, we would not have enough evidence to prove the alternative hypothesis, because 0.01899 is larger than 0.01. So we would have to come up with a do not reject the null decision. Now, Excel figures out what the sample values are. 10 is the value of B0, which is the sample y-intercept. The 5 is the value of B1, which is the sample slope. These are the sample regression coefficients. What we're attempting to do here is to estimate, well, what's the corresponding population value. Beta 0 is the parameter that corresponds to B0. Beta 1 is the parameter that corresponds to B1. You can take the sample value and add and subtract the margin of error, and you can come up with the confidence interval estimate. Now, by default, Excel is going to give you a 95% interval estimate. When you do the regression, if you want 99%, just check the box there next to confidence, and then inside the box change the 95 to 99. You'll still get the 95%, but you'll also get the 99%. If you just take the default, you'll get the same information twice. You can see here that the low 95% in column F, and there's another one over in column H, it's the same number. It's just doing the same thing twice because it's doing the default. It's doing the 95%. But we're 95% confident that the population y-intercept, that beta 0, is somewhere between 2.5 and 17.5. Now, the intercept is the value that you get when x is equal to 0. So if there are no TV ads, we're 95% confident that that population y-intercept is somewhere between 2.5 and 17.5. If we don't buy any ads at all, we still expect to sell between 2.5 cars and 17.5 cars. Now, if we buy some ads, how many cars are we going to get per ad? Each additional ad is going to correspond to how many additional cars? Well, we're 95% confident that that value is somewhere between 1.6 and 8.4. Now, what you're going to have to do is to look at, well, how much profit do I get when I sell a car, and compare that to how much money it costs you to buy an ad. There's not, on the low end, there's not that much difference between the two. So me, I'm a kind of a risk-averting type of individual. Unless my profit exceeds how much it's going to cost me for the ad, I'm going to have to think long and hard about whether or not I would want to do this. Now, this slide shows the calculations in the analysis of variance table. This is the central portion that's in the basic output that's put out for regression using the tool, the regression tool in Excel. The ANOVA just stands for analysis of variance. DF stands for degrees of freedom. SS stands for variation. Actually, the SS stands for sum of squares. MS stands for mean square, but the numbers in that column, they're all variances. And all you have to do to calculate a variance is to take the variation, take the SS value, and divide it by the degrees of freedom. Your F statistic is the ratio of the variance that's explained by regression over the variance that's due to the error, the unexplained part. Sometimes it's called residual. The formula for the degrees of freedom for regression is just 1 because there's only one independent variable. If we were doing multiple regression, then the number that would be in there would represent the number of independent variables that were used in the regression. But in simple linear regression, there's just 1, so that's always going to be 1. The degrees of freedom formula for the residual, or for the error, is n minus 2. And the degrees of freedom for the total, well, all the total is the variation in y. And since that's one dimension, that's just one variable, you're going to have n minus 1 degrees of freedom. So n was equal to 5 in this case. So we're going to have 1 degree of freedom for regression. We'll have 3 for the error. And then there's 4 total. Now there's an additive relationship among the degrees of freedom. If you take the degrees of freedom for regression, and if you add that to the degrees of freedom for the error, you'll always get the total degrees of freedom. Now that same additive relationship is going to work in the SS column. When you add up the variation that's explained by regression, the SSR, to the part that's not explained by regression, the SSE, this is the error part, you're always going to get the total. But the total is just the variation in y. So if you're given the total variation, and if you know what the error variation is, all you have to do is subtract to get the part that's explained by regression. And I think that's the way that they explain it in the textbook. To get that next column, to get the MS column, all you do is just take the SS value and divide by the degrees of freedom. So for the error, you take the 14 and divide it by 3 and come up with 4 2/3. It's kind of a unique situation when you deal with the variance in simple linear regression. The variance and the variation, they're always going to be equal because you just have 1 degree of freedom. But to get the F statistic, you just take the MSR, the variance that's explained by regression, and divide it by MSE, which is the variance that's due to the error. In this case, we're coming up with 21.4 approximately. Now, the p-value that you're going to have for the ANOVA table, for the F statistic, it's always going to match up the p-value that you have for your independent variable. If you look in the coefficients table and look at the row with the TV ads and go out to where the p-value is, that number there is always going to match significance F that's in the ANOVA table. Now this only works like this for simple linear regression. It doesn't really test the same thing in multiple linear regression, but you can use that relationship in simple linear regression. Now if we wanted to know if there's a significant linear relationship between the independent variable and the dependent variable, we can tell that just by looking at the significance for the F. You take that number, that's a p-value, you take that number and compare it to alpha. If that number is less than or equal to alpha, well then there's a relationship. If that number turns out to be larger than alpha, well then they're not related. Now the portion of the Excel regression that's up at the very top, the regression statistics, here's some of the formulas you could use to calculate these numbers. The multiple r is just the square root of the r square. It would be the correlation coefficient, except it doesn't have the sign associated with it. You're going to have to go down and look at the slope and see what the sign is for the slope to tell whether or not your correlation coefficient, whether it would be positive or negative. The definition of R squared, which is also called the coefficient of determination, is SSR over SST. Now SST is always going to be the same thing as SSY. Y is what you're trying to predict. It's what you're trying to estimate. So in this little example, what we're trying to do is to predict the number of cars sold. Now there's going to be a certain amount of variability in that data set. SST, SSY is the same thing. So the 114, that's all the variability that's in cars sold. SSR is the portion that's explained by regression. So when you take that ratio represents the part of all of it that's explained by the regression model. So in this case, there's almost 88% of the variability in the number of cars sold that you can attribute to the linear relationship between the number of TV ads and the number of cars sold. But that's a pretty meaningful statistic by itself. The correlation coefficient is up above 0.9. In this case it's positive because the slope is positive. But that indicates there's a strong relationship between the independent and the dependent variable. Now you're not responsible for the adjusted R squared. Just for completeness, I put the formula in there for that one. It's going to be a little bit smaller than what you're going to have for the R squared value. But you don't really use it in simple linear regression. It's a meaningful statistic when you look at multiple regression so that you can compare one model to another one. But in simple linear regression, you don't really need it. Standard error, this one's actually referred to as the standard error of the estimate. All you have to do is to take the square root of the error variance, which is also MSE. But you take that square root and it's about 2.16. Now what this number represents, it's the typical error that you expect to make when you do a prediction. When we try to take the number of ads and predict the number of cars sold, we expect to be off about 2.16 cars. And then observations, that's just your sample size. Now rather than explain this one in terms of the cars sold and the TV ads, what I want to do is to interpret this based upon a generic description. We just have an independent variable, we have a dependent variable. Observations tells you that there were 5 values in that data set. The R squared value tells you that 87.7% of the variation in the dependent variable may be attributed to the linear relationship between the independent and the dependent variables. The standard error of the estimate tells you that the typical error that you expect to make when you try to predict the dependent variable based on the independent variable is 2.16 units. And the units are whatever the units are on the dependent variable. The next 3 slides show the steps for producing a scatter diagram in Excel. It's using the data for the TV ads and the number of cars sold. This step 1, 2, 3, and 4 here is selecting the data, going up and picking on the particular chart. You want the scatter chart, and then generating an initial graph that you can edit thereafter. I built a little video to actually show you what the chart would look like if you followed these steps. But if you look inside the videos section of the chapter 12, it'll show you how these steps, what kind of chart it's going to generate. It doesn't look like the charts that are on these slides. Now these steps are to edit the scatter diagram. You just click on the placeholder for the chart title, and then you can type in read auto sales estimated regression line and make that the title. The chart elements, if you look to the right hand side, up at the top right hand corner there's a plus. and just click on that plus, and that lets you go after the different elements inside a chart. You just put a check mark in there for axis titles, and you'll get two placeholders for those. There's one for the vertical axis and one for the horizontal axis. By clicking on grid lines, it removes them. And then click on trend line, it will add a trend line to the graph. Then some more editing. You go to the horizontal axis title. I think it actually says value in Excel 2016. It doesn't say category, but it's just down at the bottom. And then just click on that placeholder and type in TV ads. And same thing, the vertical axis, which is kind of up and down. Just type in cars sold once you've selected that. And then you can go into the format trend line option. You can access it by going through the plus that's up at the top right hand corner on the chart itself, and go down to trend line. And when you move across trend line, you'll get this little kind of a triangle at the end of it, and just click on that and go down to where it says display the equations down at the very bottom, and you can put a check mark in there. You can also get the R-square value to be calculated for you that way also. The fill in line part is just the little fill bucket up at the top. You can click on that, and then you can format the line. And down probably, I don't know, 2/3 of the way down, there's a dash type, and you just select the very first one, which is a solid type. And then you can close the trend line, and you'll have the chart. But it doesn't really look like the chart that's on the next slide. If you look at the little video, you'll see what these steps, what that chart's actually going to look like. And then I show a few other things inside the video, how you can kind of dress up the chart a little bit. Now by default, those little markers, here you're seeing diamonds. There's circles when you just do it by default. I think they're in blue, and here they're in red, but you can change the colors of the markers. The little video, I put the R-square value in there. I think that's on the next slide. But the font by default, you're going to get Calibri, and I believe this is Arial. I think that title's in Arial. I think the axes are in Arial. Pretty sure the numbers are in Arial. The colors for those numbers, the colors for the axis titles and the chart title, there's a white background, so they're showing up in a dark color. So you'd have to change the background to make it dark, and then you can change the font color to white to make it look more like this. But all this one is showing is that regression equation. And this one, in addition to the regression equation, it's also showing the R-square value. Some of the homework problems, those are really the only two items that you might need. So you can just select the data and get it to generate the graph, and then just go to the trend line on the chart elements. Just go to the trend line, and then go down to the more options and check the box for the equation and check the box for the R-square. And you can have those numbers, and you don't have to go through the regression part. Just a couple of more things here, and then we'll conclude the chapter on regression. One of the homework problems is to generate a residual plot, and I've put a video out there, and I think I'm using the data for that particular problem to show you how to use Excel to generate that residual plot. You could do it as a scatter diagram, but you'd have to do extra work in order to do it that way. And it's just a matter of checking a box when you do the regression, and Excel will do it for you. The other thing I want to mention is a relationship between the t-test and the f-test. In simple linear regression, they're equivalent. If you take the t-value, now the one I'm talking about is for the independent variable, the one for the slope, when you're testing the slope, not the intercept, the slope. When you take that t-value and square it, you get the f-value. So the p-value for the f-test, it's not labeled as a p-value. It's labeled as significance f. But that number is always going to match the p-value for testing the slope, not the intercept, but testing the slope. So if you run into a homework problem when they say, what's the p-value for the f-test? Well, just figure out what it is for the t-test. It's a two-tail test when you do it for a t. It's a one-tail upper tail test when you do it for an f, because of that square relationship. But this concludes the regression and correlation aspect of the course.